So it is my very great pleasure and honor to introduce today's speaker at the seminar, The Analysis and Methods of PDEs. It is Professor Isabelle Gallagher from the École Normale Supérieure in Paris, where she has been a professor since 2017. Previously, she was a professor at Université Paris Diderot. She is very well known for her foundational works in the study of the mathematics describing systems of gases and fluids, and particularly for her work in the derivation of Boltzmann equations and kinetic equations from interacting particle systems. For her work, she has been honored with numerous distinctions, including the Erwin Schrödinger Medal, the Prix Sophie Germain from the Académie des Sciences, Silver Medal from the CNRS, and many other honors. So it is a great pleasure to introduce Isabelle, and she is going to talk about the dynamics of dilute gases today.
Thanks very, very much for this introduction. I'm really very happy to be able to give a talk in this this webinar. So yeah, as it was said, I think in the chat, please feel free to stop me whenever you like in this talk, either by writing something in the chat, and I'll check it once in a while. Maybe Tom can check that out, or just by speaking up. I'll be very happy to answer any question. Yeah, so this talk is about the dynamics of dilute gases and maybe also fluctuations and large deviations. I think that was the original title, so sorry I changed the title on the way. Maybe I should just apologize in some sense for some people here who've seen some of the parts, at least, of this talk before. So yeah, I'm sorry you might get bored, but I guess this is a general PDE audience probably. So as this subject gets sometimes very technical, I'll try to keep it the technicalities not too high, but then maybe some will be frustrated. So please ask questions if you like at any point, if you like. So yeah, so this is a project that's been going on for many years now with so myself with Thierry Bodineau and Laure Saint-Raymond and Sergio Simonella. So we are trying to understand in some sense how you can derive macroscopic equations starting from the dynamics of particle systems, which would be deterministic, right, which would satisfy Newton's laws, which we'll be writing down in a second. And so roughly speaking, I mean, there is a way to do that in a formal way. It's pretty clear how you could derive the Navier-Stokes equations using the Boltzmann equation as an intermediate model. But what's difficult is to make this into theorems, as I'll try to explain, the reason why I'll try to explain. And so what I'll do in this talk is first try to explain how to derive the Boltzmann equation, why there are some problems in getting it as you would like, getting the best theorem you'd like. And I won't really explain how to go from Boltzmann to fluids, which is not the topic of my talk, not even, well, really my specialty, although I've tried to do that sometimes. It's not really what I want to explain today. But what I'll try to explain is one way of improving things might be trying to understand better the limit from particles to Boltzmann. So that's sort of what I try to do today. Understanding it better, meaning understanding fluctuations around the Boltzmann equation and in some way a large deviation. So I'll try to get to that by the end of the talk. But let me just start with the basic equations for the particle system. Okay, so essentially what we're looking at here is a gas. We'll see in a few minutes why it's dilute, but for the moment, let's just assume you're given a gas or a fluid. So you've got lots of particles, which are very small, and what you know is that they're always moving, right? Even if the gas which you're looking at seems to be at equilibrium, so it doesn't seem to be moving, each particle is moving. And so the question is how to relate the movement of each particle to fluid mechanics equations, like the Navier-Stokes equations, okay? So, right, so I'm looking at a glass of water, I'm looking at the air in the room where you are, and I'm going to write down equations for each individual particle. And to do that in the easiest way, so physics is sort of leaving the picture here, I'm just going to assume each particle is a hard sphere, they're all identical. Okay, so this is the picture you should have in mind, that you're given, let's say, capital N particles. So the notation I'll try to use all the time here is N will be the number of particles. I'll give them numbers, okay? But of course, everything should be invariant through the numbering. I'm just labeling the particles just to follow them, but everything has to be independent of that, of course. So I have particle I, particle J, all are between 1 and N. The diameter of my particles I call epsilon, okay? So it's very small, right? The number of particles is going to be very large. And the equations on each particle will be the following. So let me assume that they're all identical, mass 1, to make things as simple as possible. So I'm even going to assume there's no force acting on my system. Okay, so the acceleration of each particle is 0. V here is the velocity of each particle. So each VI, you should think of it as a vector in RD. D is 2 or 3, roughly, in general. And each xi here is the center of my particle, right? They're all spheres. So xi will be living for this talk in the torus, okay? A lot of what I'll say is true in the whole space, and hardly anything I'll say is true in any other situation. We can discuss that later on, okay? So, or whenever you like. But for the moment, let's just fix the center of my particles to be called xi in the torus. The velocities are in the whole space, and they're related by Newton's laws. Okay, so the time derivative of the position is the velocity, and the time derivative of the velocity is the acceleration, and I'll just set it to be 0. So that, if you just look at those equations here, that just means my particles are moving in straight lines, right? Velocity vi, which is constant. But then, of course, what happens in real life is that they're going to collide. And for today, and for most of what's known actually for the Boltzmann equation, I'm going to assume that they collide just like billiards, a perfect billiards. Meaning at collision, I have conservation of momentum, which is here, and conservation of the energy. Okay, so notation for the whole talk. If I'm given two outgoing velocities, which I call VI and VJ, you can compute VI and VJ with respect to V prime I, the incoming velocities, and V prime J by this formula here, which is an involution, right? You can put primes wherever you like here, right? So of course you don't have to remember the formula. All maybe you want to understand here is that omega is the unit vector relating the centers of my particles. Okay, so omega is of size 1. So with respect to epsilon, of course, it's very large. That's omega. And it's relating the centers of my particles here. Okay, so the laws I've written here, the relations here are just the usual specular reflection relations. You don't have to remember them, but maybe you can just remember that I'm looking at a perfect collision or elastic collision where you have conservation of energy and momentum. Okay, so this totally defines your system, right? I mean, you're given exactly, if you know how to solve the system, you know everything about your system. Except that for the fact that you really don't care actually about where each particle is at each time, right? And what its velocity is. Us human beings, we don't have any access to the molecules or to particles. We have access to wind, we have access to temperature, and these are sort of average quantities. As I said before, your gas can be at equilibrium, but all the particles are moving. So what's the relation between the fact that my gas is not moving at our scale and the fact that all particles are indeed moving? So that's the rough question I want to ask is, how can you relate this huge system of equations? You have n particles, that means 6, sorry, is that 6n? Yeah, in dimension 3, it has 6n equations, right, for position and velocities, and then they're related by the collisions. So this is a very difficult system, a huge system. And the question is how to extract from this system, by some kind of an averaging procedure, an equation you can use, roughly the Navier-Stokes equation or the Euler equations. Okay, so one thing I want to say here also is that this system of equations is time reversible, right? Because if I change time t into minus t, then you just have to change all velocities into minus the velocities and you get exactly the same system. Okay, so this system is time reversible. But as you might know, the incompressible Navier-Stokes equations are irreversible, right? Because there's a diffusion, like heat equations, irreversible. So one thing we also have to understand is how to get an irreversible equation starting from a reversible system of equations. That has to be understood at some point if you want to write anything. So yeah, so that's the plan, is how to extract some effective equation, which will be irreversible, from that gigantic set of equations. And also, as I said, this set of equations for each particle doesn't seem to be what we understand, right? So that's why we want to find this effective equation. So this actually was the question raised by Hilbert in 1900. That's his sixth problem. He was asking how to develop mathematically the limiting process which leads from the atomistic view to the laws of motion of continua, meaning go from Newton to Navier-Stokes. Okay, by some limiting process. Obviously, if you only have two particles, you're not going to get fluids. You're not going to get Navier-Stokes. So you have to take into account there are a lot of particles, have some kind of limit as the number of particles goes to infinity, some kind of averaging procedure, which will give you, for instance, Navier-Stokes. And actually, what he also suggested, and what we're going to do in a second, is to use Boltzmann's vision of things, which is a mesoscopic scaling, to go from microscopic to macroscopic. Try to use the Boltzmann equation somewhere in between. So that's what we're going to do right now, actually. So we're going to follow Boltzmann's idea, intuition, which was to say, one thing you could try first to study as time evolves is not the position of each particle, but more how many particles will be at time t at some position x and some velocity v. Okay, so we call that mesoscopic. It's not yet a function just of time and space, which this is what we will be interested in the end. Okay, I just want to know if I look at some point in space at time, what's the pressure, what's the temperature, what's the velocity of my fluid. For the moment, we don't do that. We just say, let's fix time, fix x and v, and see what's the proportion of particles, what's the density of particles at position x plus dx, velocity v plus dv at this time t, right? So this distribution function f is going to be a solution to the Boltzmann equation. That we have to understand. But again, this is not exactly the fluid we're interested in. It's not macroscopic yet. If you want to get a fluid equation, what you'll have to do afterwards will be to integrate, to average this quantity with respect to velocity. Okay, so if you, for instance, if you take your f here and you integrate against all velocities, dv, in the whole space, this is going to give you a density in time and space. Okay, that will be the density of your fluid. If you integrate against v dv, this will be a velocity, the average velocity of your fluid. Okay, and then if you integrate against v squared, this will give you some kind of energy or temperature. Okay, and these things we can measure. So the plan now is to understand, given the Newton system of equations, can I write down an equation on f? Okay, so f is living in a much smaller phase space. It's just x is in the torus, v is in RD. So it's just one function on time, space, and velocities. And once I've done that, can I write down equations for the macroscopic quantities, which are density, velocity, and temperature? So let me start by just giving you the Boltzmann equation. Okay, we'll try to understand later on why that's the correct equation, but here is the Boltzmann equation. So I guess a lot of you have seen it before, maybe not all of you. So just let me spend a minute just running through this equation to try to understand each term. Okay, so sorry for all those of you who've studied this more than me, but I guess it's important for all of us to understand what that equation is telling you. So essentially what it's telling you is the following. Just look at the left-hand side. This is a transport equation, right? If you have 0 on the right-hand side, this is telling you that the density of particles at time t with velocity v in position x, you just computed by pulling back the density at time 0 by x minus vt. Okay, it's just pure transport. But of course, my particles are not going in straight lines, so you have to take into account binary collisions. I've only talked about binary collisions, so the right-hand side here will be quadratic. Okay, that's because I'm just looking at binary collisions between particles. And so the right-hand side is going to tell you what's going to happen, what has happened in your fluid or in your gas, so as to create a particle with velocity v, position x at time t. So when I'm saying creating a particle, I'm not just creating actually a real particle. I'm just saying I have a particle with velocity v and position x. Okay, this particle suddenly has taken velocity v at position x. So how can that happen? Well, this can happen because what can happen is that a particle of velocity v prime is going to hit a particle of velocity w prime for any w in the whole space. So that's the RD here. I integrate against any w. And this, by collisions, will create a particle of velocity v. Okay, and that's given by this relation here. These are exactly the scattering relations we saw before. Omega is any vector, random vector on the sphere. That's why I integrate against every possible unit vector. And this product here is telling me if a particle of velocity w prime hits one of velocity v prime at position x, well, this creates a particle of velocity v at time t and position x. Okay, so this accounts for this bilinear term here. Okay, and what can also happen is that a particle of velocity v hits a particle of velocity w for any w. Okay, and this creates another particle, well, a particle with a different velocity, I should say, hence the minus sign here. Okay, so the right-hand side of the Boltzmann equation is telling you how you can suddenly get a particle of velocity v by a collision, or you can lose a particle of velocity v by a collision. So I hope this is a sort of reasonable, that this explains these two terms with a plus sign and a minus sign, because F is a probability density, so it's non-negative. And now the last thing I might need to explain is this guy here, which we call the cross section. And so I can't really explain where it comes from. We might see it a bit later, but for the moment, let me just explain that if this is 0, that means actually Q of FF, there's no contribution to this Q of FF. This is 0, means that the relative velocity of my particles is perpendicular to their relative positions. Meaning, if you imagine my two particles, they're going in straight lines, okay, and they're going in a parallel way, okay, because their relative velocity is orthogonal to their positions. Okay, so that's why you get 0. It's normal. There's no collision, actually. They're just grazing. And on the other hand, this is maximal if my particles, their relative velocity is parallel to omega, meaning they're just having a head-on collision. Okay, so I'm not proving this is the right term, but it's sort of reasonable. Okay, so this is an introduction, crash course to the Boltzmann equation. Here it is. Maybe before I explain in a few lines how you obtain this equation formally, for those of you who've never tried to solve it, we could maybe just spend a few minutes trying to solve it, or at least I'll give you theorems saying, given F0, there is F. Okay, that's the best thing you want to do when you have a PDE, you want to solve it. Okay, and if you want to solve it, the first thing you want to understand are what are conserved quantities. That's one thing. What are stationary solutions? Okay, because if you have a stationary solution, then you can try to solve the equation around the stationary solution. Okay, so how do you get a conserved quantity? Well, one thing to do is to try to write an energy estimate or try to find something which has a sign. And so the thing that you should do, perhaps, is take your function f, multiply it by anything. Okay, let's say, because I know the story, let's say that it's anything phi is smooth and depends only on v. Integrate that against v and try to compute the time, or even against x also, and compute d over dt. If you get 0, then that tells you that f phi is conserved. That's good. It won't blow up in finite time. It's a good quantity to study. And for this to be 0, what you actually need is for q of ff, phi of v, dv dx to be 0 for any f. Okay, so question, when is this q of ff, this crazy guy here, I multiply it by phi of v, I integrate over v, and maybe over x, I want this to be 0 for any f. So let's do that. I take my q of ff, I multiply it by phi, that means here I put a phi of v, I integrate over v, okay? And then I notice that since I'm integrating over v and w, everything is symmetric with respect to v and w. Okay, so I could very well put 1/2 of phi of v plus phi of w, that would still be the same. Okay, then I also notice that I'm almost symmetric, I'm skew symmetric with respect to changing vw into v prime w prime. If I do that, I'm changing all the signs, so I get 1/4 of phi of v plus phi of w minus phi of v prime plus phi of w prime. This is what I get. Okay, so for any function phi, formally, q of ff times phi is equal to this integral here. So now the question is, when is this integral equal to 0 for any f? Answer, if phi is equal to a constant, then I have a constant 1, for instance, 1 plus 1 minus 1 minus 1 is 0. Okay, so that works. And now I know because of conservation of momentum, if phi of v is equal to v, then I have v plus w minus v prime minus w prime, that's 0. Okay, if phi is equal to v squared, then I have the same thing because of the conservation of energy at the microscopic level. So through the scattering, I get this. This is also 0. And then there's a theorem saying that that's the only possibilities. So q of f times phi is equal to 0 for any f, if and only if, under very weak regularity assumptions on phi, if and only if phi is either constant, linear in v, or quadratic in v. Okay? This is what's here. Right, so what I'm just saying here is that actually the integral of f is conserved through the equation, which means mass is conserved. The integral of fv is conserved, momentum is conserved at a mesoscopic scale, and the integral of fv squared is conserved, the energy is conserved, if you integrate over x and v. Okay, so that's the first thing you can try to use to solve the equation. It's not very much, right? It's not a lot of smoothness, not a lot of regularity, not a lot of decay, but at least you have that with you. Now, the last exercise you can do is, which Boltzmann did, is say, okay, let's set phi of v to be equal to log of f, actually now of x and v. Okay, so choose phi to be log of f formally. Then you have the sum and the difference of 4 logs, which is the same as log of f of v times f of w divided by f of v prime times f of w prime. And then using just growth properties of a logarithm, you get that actually q of ff times log f is non-negative. Okay, sorry, non-positive. So that's the H-theorem. Entropy of solutions of the Boltzmann equations decays with time. Okay, that's really important because that's a quantity you have under control for all times. It even decays. This is telling you 2 things. It's telling you should use the entropy to solve the equation because it's under control for all times. And it also tells you that the Boltzmann equation is irreversible, right? Since this quantity is decaying in time. So if you change t into minus t, it will increase. So it can't be a solution. If you change the arrow of time, you can't be a solution of Boltzmann because the entropy should decrease. Okay. So here we've already seen something irreversible. I told you at the very beginning, we want to find Navier-Stokes, which is irreversible. Actually, even Boltzmann is time irreversible. Okay, so that was a very big problem when Boltzmann derived this equation, because people were saying, how in the world can you start from a reversible equation and just find at some kind of limit something which is irreversible? It can't be true. Okay, so that was a big paradox at the time, which now we can understand very well, but at the time it was really a very big problem. Okay, so that's one thing you should try to remember. Conserved quantities, that's essentially all we know, I guess, about Boltzmann in terms of conserved quantities. And then I told you maybe we could also try to find stationary solutions. So obviously 0 is a stationary solution. Okay, no problem with that. And then there's another one, and one way of seeing of guessing the stationary solution would be, to be stationary, I need the entropy to be constant, right? If my solution is stationary, everything is constant, so the entropy must be a constant. So in particular, q of ff times log f must be a constant if f is stationary, which means log f has to be 1 or v squared. And since f is also in L1, because it's a probability density, that means f has to be a Gaussian in velocities. Okay, so you can check easily that the Maxwellians or Gaussians, here I took the simplest one, are stationary solutions to the equation. Okay, so now solving Boltzmann, which is a nonlinear PDE, as usual, you can do 2 things. You can either try to solve it globally using conservations, or solve it maybe only locally, but using that you're close to a Gaussian. Okay, and that's essentially what's known to today. So these are really not the best theorems that are known, but this is something we can try to remember maybe for what follows. Is so the first theorem you can prove is if your initial data is, let's say, continuous and decays fast enough at infinity, like a Gaussian, then you can solve uniquely your equation. It's on a short time, okay, t positive. And this short time will be, I mean, the blockage in solving the equation is when you no longer get a decay like this, okay? So if you just plug that into the nonlinear term and try to write a fixed point or something, because the cross-section has a v, you're losing v's in your estimates. That's why this decay is getting worse and worse with time. You use some kind of a Cauchy-Koretskaya argument. And so, for instance, in time 1, whatever, 2 will become 4, and then 8 and 16, whatever. And at some time, you have to stop your fixed point. Okay, so the fixed point breaks down because your decay is going to be linear in time, essentially. Okay, this beta 0 will decay linearly in time in some sense. And so at some point, you have to stop. Okay, so one way of getting a global solution in this setting is assuming that you're close to an equilibrium, actually also close to 0. But close to a Maxwellian, which is probably more reasonable maybe physically. If you're close to a Maxwellian, then very close, then you have a global solution, which is unique. That's a typical well-posedness result for a nonlinear PDE, evolution PDE. And then now if you say, okay, let me forget about this, let me use the entropy, then you can prove there are global solutions. They might not be unique, I don't know, no one knows if they're unique. They're not exactly solutions, not even actually distribution solutions, they're renormalized solutions. That's due to Ronde-Perna and Convergence in the late 80s. Okay, finite entropy initial data, you get global solutions in some sense, but we don't know if they're unique. Okay, so this won't be used in the following, but you can just remember there's an issue with time here. The Boltzmann equation, you only can solve it, let's forget about entropy because it's hard to use at a particle level. You can only solve the Boltzmann equation for short times for smooth enough and rapidly decaying initial data. This is definitely not the best theorem you can prove, but it's essentially what we'll be using in the following. Is that okay for the moment? So shall I move on? So this was just a crash course on Boltzmann. And what I promised was to tell you that Boltzmann does converge in some sense to fluid mechanics equations. So again, I won't be even stating actually any theorem here, but just telling you what's the recipe to get fluids. So the recipe is to introduce in your equation the mean free path. Okay, so we might see later on when we derive in some sense the Boltzmann equation from particle systems, that if you remember that there is a mean free path in your problem, which I'll call alpha here, then actually what pops out in your equation is this 1 over alpha here. Okay, physically this does arrive in the equation. I didn't put that before, but actually physically you do have the scaling here. Okay, and finding fluid equations means I want this mean free path to tend to 0. Okay, so now the solution to the Boltzmann equation depends on this parameter. The very bad news is that the lifespan of the solutions we've constructed before is of the size alpha. Why is that? Because as often when you want to solve the equation in a unique way, you write a fixed point. At some point, you totally forget that Q of FF is anything different than F squared. Okay, and if you solve DTF is equal to F squared, then the time lifespan is 1 roughly. If you solve DTF is equal to 1 over alpha F squared, lifespan is alpha. Okay, so that's why, that's not a proof, but that's the idea behind the fact that if I put the scaling here, this equation a priori has a solution only on a time alpha. Okay, for a size 1 initial data. Right, but now if you start linearizing or writing F is equal to a Gaussian plus alpha times something, then it's on this alpha times something, on this something you're going to work to get fluid mechanics equations. Okay, that's the idea. So you're close to a Gaussian. And so, okay, so that's what's the plan? What I'm going to do now is let n go to infinity, number of particles, their diameter goes to 0 for everything to fit in the box. And as I said before, I let the mean free path go to 0. Okay, and now what we expect, what we want is to go from my molecular dynamics to hydrodynamics. So what I need to set here is the number of, is the way these guys are converging to infinity or to 0. I mean, everything depends on everything. Okay, so let's see what the scalings should be. Right, so scaling should be the following. So this is sort of the only way to make things work. So let me try to explain a little bit how this works. So this picture in the middle is telling you this is a given particle of diameter epsilon. If I let it evolve in a time t, if its velocity is v, okay, then if it doesn't cross any other particle, it's going to occupy a domain of size roughly tv, maybe tv, yeah, roughly to d maybe, times epsilon d minus 1. Okay, that's the volume occupied by this particle in time t. Okay, and now my mean free path, as I said, was alpha. The relation between the mean free path and the number of particles is that I have n minus 1 particles around me. Okay, let's say n is equal to n minus 1 when n is very large. So to be sure that the mean free path is essentially of the order of alpha, then I need the number of particles times the volume occupied by my particle in time 1, let's say, to be equal to 1 over alpha. Okay, that's a scaling condition, right? So what I'm going to do here is let n go to infinity, let epsilon go to 0 with this scaling, which we call a Boltzmann-Grad scaling or a dilute gas scaling. So if you like, you can start by taking alpha equal to 1. If you don't want to get fluid dynamics, take alpha equal to 1. You want this n epsilon d minus 1 to be equal to 1, right? But actually what I want is the mean free path. So I need actually this to be going to infinity since alpha is going to 0. So what you notice here is that I have a dilute gas because n times epsilon d is very small, okay? But n times epsilon d minus 1 is size 1 of alpha, so over alpha, so it's going to infinity. Actually, it's pretty large if alpha is very small. Okay, so let's just try to remember the scaling if you don't mind. And epsilon d minus 1 is equal to 1 over alpha. Alpha is the mean-free path. Right, so can we do that? Can we do this program going from Newton's laws to Navier-Stokes? So the answer, to my knowledge, is roughly a no, not directly, unless you put some noise in the Newton's laws. For instance, if you decide that when two particles meet, then the reflection condition will be random in some sense. Okay, you put some small randomness in your system, then that helps in some sense because you get some kind of ergodicity, and it's possible, it's hard work, but it's possible to recover compressible Euler or Navier-Stokes equations by this method. Okay, so I won't be talking about this at all because it's not exactly what we're trying to do. What we want to do is go from a deterministic system of particles to Navier-Stokes. Okay, so it's a little bit different and much less is known, and that's what I'll try to explain in the time that's left here. And so again, the idea is to use Boltzmann, right? So I start with my Newton's laws. I'm going to let n go to infinity, epsilon go to 0. With this scaling, and alpha is fixed, so just take alpha equal to 1 if you like, and you get, we hope to get the Boltzmann equation. Okay, once you've done that, then you say, right, now let me let alpha go to 0 and let me get fluid mechanics equations. Boltzmann was saying that's possible. So actually there are quite a few results on the limits from Boltzmann to fluids. Okay, so here are some references among others, where you can get either strong solutions, weak solutions. So if you're interested in that, we can discuss that whenever you like. But for today, as long as you don't ask me, I'm not going to use this. I'm just going to take that as a black box. I'm going to say, if I'm able to go from particles to fluids, then I can plug, sorry, from particles to Boltzmann, then I plug in that proof those results here, and I get particles to fluids. Okay, so my worry today is to go from particles to Boltzmann. And then I'm going to use these results, which are known, telling me then you can go from Boltzmann to fluids. Is that okay? That's the plan. Right, so unless you ask me more question or any question about Boltzmann to fluids, let's skip that. Just say, okay, assume that's known. Now let's go from particles to Boltzmann, and then we'll just use known results to recover the fluids at the end. Okay, so this is the, I guess, now getting more technical, so I'm sorry about that, but I'll try to go slowly and explain the notation and stuff. But let me try to explain to you in a few slides how you derive, honestly, the Boltzmann equation. Okay, I just gave you the Boltzmann equation. I tried to explain why it was reasonable. Now let me show you where it comes from. And so what you're going to do is start averaging on stuff. So what am I going to average on? I'm going to average on the number of particles. Remember, I called capital N the number of particles. I'm going to assume its expectation, in a sense I'll define in a second, is this guy mu epsilon, which is epsilon minus d minus 1. So this is, so 1 here will be 1 over alpha one day, but for the moment, and even for the whole day, I won't be using the limit Navier-Stokes, right? So alpha will be going to 0 later on, but since I don't want to use this limit, because that's not my point today, I'll just take alpha equal to 1. Okay, just for today. Almost always today. So that means this is just telling me that's the Boltzmann-Grad scaling. The expectation, in some sense, I'll define in a second, of the number of particles is exactly epsilon to the minus d minus 1. That's Boltzmann-Grad. Okay, so that's just the number of my particles. It's a random parameter, which is distributed along like a Poisson distribution. Okay, this is this W0 here is the probability of having small n particles at configuration Zn. Z here is a collection of all positions, velocities. Okay, some notation, sorry about that. So my phase space, so all positions, all velocities, is the torus times Rd. We saw that at the very beginning, to the n if I have n particles. And of course, I need to remember that particles aren't allowed to overlap. Epsilon is the diameter of my Hart spheres. Okay, so in terms of the phase space, this translates the fact that particles don't overlap. Okay, and now what's the initial probability density? It's given by the following. My particles can't overlap. That means the configurations are sitting in this phase space. The number of particles, the average is this mu epsilon, which is epsilon minus d minus 1. And then all my particles are identically distributed according to some F0. Okay, so this is, and then of course I normalize everything for everything to be of norm of for this guy here to be a probability distribution. Okay, so from now on, if I say some expected value, what I'm saying here is actually I'm summing over n, I'm integrating over Zn against this distribution here. Is that all right? Okay, so the only probabilistic or statistical part of this talk is this. I don't know that where my particles are. I just say they're just all distributed according to F0. I don't know how many particles I have, but they're all Poisson distributions, and I know the average is 1 over epsilon d minus 1. Okay, and now everything I'm going to do is averaging out against this initial probability density. Okay, that's what I'm given. I can only play with F0. F0, of course, will be the initial data of Boltzmann, we hope. And now, using this, I want to derive the Boltzmann equation. Okay, so the first thing you should wonder is what happens to this initial probability density as time goes on? Well, that's pretty easy. It just satisfies this transport equation. Okay, why? Because particles are transported. Okay, so at time t, the probability of having n particles at some configuration Zn is this transport equation set in this, again, phase space, right? No overlap. Now, if I have a transport equation in a bounded or, in a domain with boundaries, I have to put boundary conditions. And my boundary conditions will be given by scattering, meaning if I'm giving two particles which are going out, one from the other, touching and going out, I should replace the outgoing velocities by the incoming ones through the scattering. Okay, so I have a transport equation on Wn for any n with the boundary conditions given by scattering. And now what Boltzmann says is what I want to find is an equation at the limits when mu epsilon is going to infinity for the probability distribution of one particle, not all n's, right? Because remember, your limits function f is a function of txv and not xnvn, not the whole set of particles. So what you're going to do is integrate against all the particles. And doing that is looking at the one particle correlation function, which I call here f epsilon 1. Okay, so this guy is roughly taking w and integrating it out against all the other particles except for 1. Okay, another way of seeing this is this f epsilon 1 computed against the test function h is just computing the empirical distribution with h. Okay, that's another definition of the one particle correlation function. I hope this is not too horrible. Okay, so you take the empirical distribution, evaluate it with the function h. Okay, and by definition, if you take the expected value of this guy with the definition I gave before, according to the initial data, by definition, this is the one particle correlation function. And now the goal is to prove that this guy converges to the solution of the Boltzmann equation. Okay, and to do this, it's actually formally not very hard. So let me first maybe state the theorem. Theorem is telling you the following thing: take F0 continuous, bounded just like the Ukay result before, bounded by a Gaussian. Okay, then Lanford tells you that the one particle correlation function does converge as the number of particles goes to infinity towards the solution of the Boltzmann equation. Okay, that's what you want for a short time. And the time depends on the C0, and sorry, beta 0 is beta here. Let me change this to beta 0 if I can. Okay, right. So Lanford is telling you what you want. The one particle correlation function converges to the solution of the Boltzmann equation. That's what we wanted. He also says that if you look at the n particle correlation function, which you can define in this way, now take a set of n particles at time t, evaluate that against the function hn, which is given, take the expected values, that's some kind of empirical distribution, but for n particles. This defines the n particle correlation function. Then he also proves that for any given small n, as the number of particles in average goes to infinity, then this converges to n copies of the Boltzmann equation. This is propagation of chaos. Particles become independent as the number of particles goes to infinity. Okay, so that's exactly what you want, again, for a short time. Is that all right? So let's see how this goes. Okay, so I still have a little bit of time. So I can show you how this goes briefly, and then I'll talk about fluctuation, since I promised. So let me just show you, I don't know if it's, yeah, I'm trying to go quickly through that. So the definition of the n particle correlation function is that, okay, you take your n particle, capital N particle distribution function, integrate it out against all the others, bit of scaling, and this defines the n particle correlation function. This is a definition again. Now the idea is to say, to prove Lanford's theorem, let's write down an equation for this correlation function, okay? And you want to prove that it converges to n copies of the Boltzmann equation, okay? So here, this is just a little bit of work using the Stokes formula. So I'm sorry, this is technical. About after a while, it will get better, I hope. But I have to sort of go through that. So if you write down the equation on Fn, the right-hand side is due to the fact that you're exchanging an integral with a derivative. Okay, so if you do that, you have a Stokes theorem coming in. And the Stokes theorem is telling you, well, you have to hit the boundary. And the boundary is actually meaning one of the particles in the Zns, which I call capital particle number I, is going to touch another particle, which I call particle n+1. Okay, touching means that xn+1 is sitting beside xi, and its velocity is either an incoming velocity or an outgoing velocity. So please, believe me on this. We can talk about that later on if you like. But for the moment, just remember I'm using the boundary condition maybe to write this down. This is explicit. There's no cheating. I just write down the equation, work a tiny bit, and I get this. Okay, so here it is again. Sorry, here it is. And now the idea of Lanford is to write down a Duhamel formulation. Okay, so I had a transport equation with the right-hand side. The transport operator I call S epsilon n. It depends on epsilon because it's transport with collisions. And then I have a Duhamel term. And now the idea is to say this Fn+1, I can again write down the Duhamel formulation inside this guy. Okay, so I have another term, and then I can do that again, and again, and I get this formula here. So this is a very condensated way of writing down an iterated, infinite series, infinite iteration of Duhamel formulas. Okay, so what you find here is all this is essentially there's no cheating. I'm just iterating a Duhamel formula. What I'm saying here is to compute the distribution of n particles at time t. What I do is the following. I take n plus m particles at time 0 for any m. Okay, so I have a sum here. And then I pull back by transport for a small time tm. Then I collide with a particle. I integrate. I pull back again. I collide. I integrate. I pull back again, blah, blah, until I get to n particles. Okay, this guy, remember the c was an integration against one particle. Every time I apply a c, I lose a particle. I go from n+1 to n. So this formula here is going from n plus m particles, n plus m minus 1, blah, 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 until n. Okay, so I have an explicit representation of the solution. And now to prove Lanford's theorem, all you want to do is take a limit in the series and obtain, in some sense, that as mu epsilon goes to infinity, this looks like n copies of the solution of Boltzmann's equation. If you prove that, you're done. Okay, so to do that, what you have to prove is that the series is converging, that each term of the series converges, and to check that once you've taken the limits, you do get n copies of the Boltzmann equation, which you can call a Boltzmann hierarchy. And so let me just show that in a few words. Why does the series converge? Here it is again. Well, you've probably forgotten, but this guy here looks like a collision operator for Boltzmann. So there's a cross section which costs v, and then you had a sum. So let me maybe I should show it again if you don't mind. Here it is. You had a sum here, 1 to n. So it costs n and it costs v. Okay, so each cn looks like n times v, very, very, very roughly. Okay, so each guy here looks like n times v. Let's forget about the v. We'll control by the Gaussian because the initial data has a Gaussian decay, so it will eat up all those v's. Okay, but then each of these c's here costs an n, so cn plus m costs n plus n, cn costs n. So in the end, you have this guy here. Forget about the v's, you eat them up by your Gaussian. So you already have a cost like factorial n, essentially, m, sorry. Now this integral in time is just over a sort of a, what do you call that? well, anyway, you integrate one after the other, those integrals in time. This is exactly t over t to the m divided by factorial m. This factorial eats up this one. That's good news. So in the end, what you get is something like ct to the m, and that's why you have a short time convergence. Okay, so you have short time convergence because this series is only converging in short times. There's no entropy here. You're not using anything. You're just using squares, and you're doing something very rough. That's why you have short time. Once you've done that, it's not so hard to get convergence. Why? Because you know the initial data converges to its tensor product without zeros. Collision terms, you have your x's, which are distant from an epsilon. And epsilon goes to 0. You get pointwise interactions, which are exactly q of ff in some sense. And the only maybe a little bit sort of technical thing is taking the limit of this guy. S epsilon is roughly what do you call that? A transport, but with collisions, right? There's an epsilon here. When two particles meet, they touch and they jump. Boltzmann has no collisions because particles are pointwise. So what you need to prove is that this converges to just free transport. That's only true if when two particles meet, they never meet again. Because that means once they've met once, then it's only free transport. They meet here, then free transport. So that means you have to eliminate recollisions. That's the only, well, sort of hard part of the proof. And once you've done that, you've proved the results up to checking that n copies of f is a solution to the hierarchy that you just check. And you check that you have only one solution to the hierarchy. Once you've done that, you're really done because you proved that the only possible solution at the limit is n copies of the Boltzmann equation. Okay, so again, the only hard thing in some sense is proving there are no recollisions. If not, you can't have propagation of chaos, right? I mean, if you have recollisions, that means that particles are not independent when they meet, so you don't have propagation of chaos. So you have to eliminate asymptotically recollisions. And what's interesting here is to notice that a recollision decides on the arrow of time. Because if I'm saying I eliminate recollisions, that means when I'm saying I have future and past. Recolliding means future, okay? And one way, well, there is a way of writing everything down, writing Lanford's statement and Lanford's proof in a way which is really obvious that everything is irreversible. That we did with Thierry, Lorenz, and Sergio a few years ago. The arrow of time is decided at that moment in some sense. Okay, so in the proof of Lanford, you can really see where irreversibility comes out. Notice that the short time restriction comes from the fact that I have the series, which is growing. That means in some sense collision trees are growing. And you can do the same proof at equilibrium, it will cost the same. We're unable to use the structure of the nonlinear term at this time. So that's why we have short times. And so what I want to do just to finish is to show you, not really to improve this, but to try to understand a little bit better this convergence, fluctuations, large deviations. And the idea is to say, the more I understand this proof, maybe the more we can make it better and get maybe one day a long time convergence result. Just one comment here, if I had put 1 over alphas in my equation, okay, exactly like Ukai's results and everything, the short time, which is here, would be O of alpha. Okay, so that's very bad news because remember what I want to do afterwards is to plug in theorems alpha going to 0, but I can't plug anything in because when alpha goes to 0, Lanford's theorem breaks down. Okay, because it's the time of existence, the time of validity of his theorem is alpha. Okay, so there's no way for the moment to get the Navier-Stokes equations because there's no way for the moment to improve that. So there's really a very important issue here of improving the short time restriction of Lanford because if you want to get fluids. Okay, so I'll skip the 2 next slides, so close your eyes and then open them again because I wanted to mention a tiny bit about how to do better in a linearized setting, but here it's gone. I won't do it because I don't have enough time, but just to say in the linear case, sometimes you can do better. Okay, so maybe just in the 5-10 minutes that are left, I'd like to tell you a little bit about a bit of newer stuff where we've tried to understand, again, fluctuations and large deviations around the Boltzmann equation. So, okay, so let me try to explain this in the following way. One way of understanding the Lanford theorem is to see it as a law of large numbers. Why is that? Because you can read Lanford's statement as this result here. okay, the probability under the initial distribution that the empirical distribution at H, which we saw before, minus the average is large, that probability is going to 0 as epsilon goes to 0. Okay, so let me just show you why Lanford's theorem is telling you that. That's exactly a law of large numbers, okay? Why is that? Well, because actually this difference here is exactly, as I told you, you probably forgot, but as I told you before, this guy here is exactly the integral of the one particle correlation function against H. Okay, and to prove this result, you can use a Markov or whatever inequality and say, I'm just going to compute the expectation of the square of the difference. If that goes to 0, then in particular, this goes to 0. Okay, now to compute the square of the difference, I just expand the square. When I expand the square of the empirical distribution, I get either H squared or H at 2 different points. Okay, that's just the square of this guy, minus, okay, and this doesn't depend, this is constant function, so I just get this squared. Okay, just expand everything. And now compute things and use Lanford's theorem. The first thing here is just a one particle correlation function, just one sum here, against H squared. With a 1 over mu, so this goes to 0. Okay. The second term here is a 2-point correlation function against 2 copies of H. Okay, and this I've just copied. And now Lanford tells you that at the limits, the 2-point correlation function looks like 2 copies of the 1-point correlation function. So actually these two terms cancel out at the limits. Okay, so Lanford's theorem really is telling you that the Boltzmann equation is a law of large numbers. Okay, so I hope this is not going too fast, but anyway, if you believe me on that, then question number 2, do you have a central limit theorem? Okay, how do you find a central limit theorem? Well, you define the fluctuation field. Fluctuation field is taking this initial thing I know goes to 0, okay, and scaling it by square root of the number of particles. That's a usual scaling for a central limit theorem. Okay, I hope that's okay with you. And now the natural question, does this guy have a limit? Okay, if it does, then you're looking at fluctuations. Okay, you're really upscaling things, right? This is very, very large. What's in parentheses is going to 0. Multiply that by this huge number. Do you get a limit? If you do, you have fluctuations. So it's an exercise you can do if you like to check that at time 0, everything is fine. This guy you compute, it converges in law to a Gaussian white noise. And its variance is given by this thing here, sorry. Okay, this is an exercise. One way of doing the exercise is computing this characteristic function exactly. I mean, things are easy enough and you get exactly what you want. So at time 0, you have something, which is good news. If not, you couldn't do anything. Again, it's an exercise. Now the question is, at time t, how does this evolve? Does it just stay the Gaussian white noise transported by something, or is it a little bit more subtle? Okay, so it is a little bit more subtle. Herbert Spohn had actually conjectured in the 80s that this fluctuation field converges to a solution of a stochastic PDE. It's not just initial fluctuation field transported or linearized around something, but actually with a real stochastic PDE. Some noise arrives at this scale. Okay, there's no noise initially because everything's deterministic, but at the scale of fluctuations, you do have some noise. And so this we proved. So let me show you how to do this. So remember, I told you the exercise at time 0 is to compute this guy. Okay, you can do that at time t, and you get 2 order 1 contributions, which are the first. This is what we did actually just before when we did the law of large numbers, except you had a 1 over mu. It's normal. Now I've upscaled everything, so this is order 1 now. You have the 1 particle correlation function. And you have what we call a second cubilant, which is exactly the difference between a 2 particle correlation function and 2 copies of F1. Remember, we did this computation at the level of large numbers. Now that everything has been multiplied by a square root of mu, when you do this computation, you get a mu here. Okay, at time 0, the difference between 2 copies of F and the original distribution is the difference between when 2 particles are close. It's the fact that they're close costs epsilon to the d, the volume of a ball. Okay, that's at time 0. Epsilon d times mu epsilon goes to 0 because this is epsilon minus d minus 1. Okay, so at time 0, there is no contribution of this guy. At time t, there is a contribution because precisely the difference between a 2-particle correlation and twice 1-particle correlations is the size of a tube. Because a collision at time 0 is just being in a ball of size epsilon d, but during the time interval 0t, it's a tube of size exactly 1/mu epsilon. So this is of order 1. And that's why you have a new contribution to fluctuations at time t. Okay, so let me just show you that in a few words. A 2-particle correlation function is you give yourself 2 particles at time t, you look at their collision trees until time 0. These collision trees can touch, recollision, or not. Saying that they don't touch is actually saying they're totally independent or they're not. Okay, so either they recollide, they're independent, that's F1 cross F1. They're not independent means their trees, that's a mathematical artifact in some sense. Being not independent means their trees are going to overlap. It's not mechanical, it's not the particles actually doing something. It's writing two trees are far is equal to they don't care one about the other or they overlap. In other words, you write this difference here, the second order cumulant, as recollisions minus overlaps of 2 trees. They recollide mechanically or they overlap mathematically. And this gives you a theorem. So I won't go through the theorem for lack of time, but I'll just tell you that the theorem tells you that the fluctuation field does have a limit in law, which and the limit solves a fluctuating Boltzmann equation, meaning you linearize the Boltzmann equation against the solution to the Boltzmann equation. Okay, so F is the solution you're given from the beginning. F1 means F of V1. F prime means F of V prime. So the first part here is what you would expect, maybe. You have initial data, and then you linearize against Boltzmann, because you're looking at a fluctuation. But now you have a noise, and this noise is given by a horrible formula I won't explain. It's a Gaussian field, and it's really related to recollisions. These 2 terms are exactly the recollision minus overlap I sort of sketched in my drawing. Okay, I won't give any proof. All I'll tell you here is that if you're at equilibrium, then you're very happy. You get this for arbitrarily long times. And thanks to that, even times going to infinity with alpha, which means when alpha goes to 0, which means you even get fluctuating hydrodynamics. So at equilibrium, you can really describe everything very, very well. Far from equilibrium, when F is anything and not a Gaussian, then you just get a short time result. And let me give, can I have 1 more minute, maybe, Tom, or is, yeah? Thanks. So I'll just state the last results, and then well, I'll just stop here, promise. What's a large deviation result? A large deviation result is saying, okay, Blanford is telling me the empirical distribution looks like the Boltzmann equation. Okay, the probability for the empirical distribution to be far from F goes to 0. We've seen that before, right? There's a law of large numbers. Large deviations are saying, okay, what's the probability for my empirical distribution to look like something else? Give yourself phi. Okay, what's the probability for pi epsilon to look like, whatever that means, any other function phi? You have a large deviation principle if you're able to prove that this is exponentially small, as mu epsilon goes to infinity, in terms of a functional of phi. This functional, of course, should vanish when phi is equal to f, because in that case, the probability is 1, right? So you have pi epsilon looking like f. So this guy should be 0 when phi is equal to f, and if not, it's a functional. Okay, and so what we can prove is that so this principle holds, at least for phi in some class of functions, right? Not for any phi. And this f here, as usually happens in large deviations theorems, is a Legendre transform of some functional, which satisfies a Hamilton-Jacobi equation. So this, if you know something about probability theory and large deviations, this is pretty familiar, I guess. If you do have some kind of a large deviation result, you'll have an exponential times a functional, which is some kind of Legendre transform of some kind of a Hamilton-Jacobi equation. What's sort of interesting here is that the Hamilton-Jacobi equation I'll write in a second is, of course, in infinite dimensions, so it's sort of hard to solve. We can only solve it for short times. The Legendre transform is, okay, I wrote it down here, but you'll want to know. This guy satisfied the Hamilton-Jacobi equation. And what's interesting here is that this theorem actually was known since the 90s. It was proved by Fredun Rizakalu in the case of stochastic particles. Okay, so he started with a stochastic system of particles with a finite number of velocities, I think, if I remember correctly. So at collisions, you could only you had a finite number of velocities, and when you collided, you selected some velocities to jump out, and he found exactly the same functional. Okay, and then Freddy Boucher a few years ago conjectured that that would happen also for Boltzmann, and actually that turned out to be the case, which is sort of interesting that whatever your model initially, in some sense, you get the same large deviation functional. And so if you want to look at the Hamilton-Jacobi equation, here it is. I'll stop here, I promise. Okay, I won't show you exactly how you find it, but here it is. So I filtered out the transports. That's why you don't see any transport term in the equation, because it's filtered out in some sense. And the Hamilton-Jacobi is here, right? You have two derivatives, functional derivatives, with respect to your function g here, times some ugly guy. And that's exactly the equation that Fredun had found many years back. And I guess I'll stop here, and thanks very much for your attention. I'm sorry for being a bit too slow. Too long, not too slow. Thank you.
Thank you very much, Isabelle, for this wonderful talk and presenting these very impressive results. Are there any questions from the audience?
So there's a question in the chat, Tom. So I can read it.
Yeah, I see it. Yeah. So there's a question by Alexander. Is there no initial or boundary conditions? So yeah, that's a very good question. So initial conditions there are. For my Boltzmann equation is the F0, right? My particles are all identically distributed according to F0. The initial conditions for my particle system, you give yourself along F0 with this crazy W I showed you before. And then the initial condition for Boltzmann is actually the same F0. With respect to boundary conditions, so as I said, we're in the periodic setting. You can do everything in the whole space, roughly. The only problem is that the Gaussian in velocities is not a probability distribution in RD. That's a bit of a problem. That's why we're in the periodic setting. We'd love to do everything in the bounded domain. Hardly anything is known from particles to Boltzmann. The only thing that's known are results by Théophile Dolmer, who did his PhD with me, and Laurent Devillette a few years ago. And he managed to do either a half space or, more recently, the exterior of a convex domain. So why is nothing else known? That's linked to recollisions, right? I told you the hardest part, in some sense, of Lanford's proof is eliminating recollisions, saying if two particles meet, actually in the past they've never met before. And worse than that, in the past, they've never met any particle that met a particle that met a particle that met them before, right? I mean, the whole collision trees have to be totally independent. And you see, if you're in a bounded domain, this looks very tricky, because maybe you can prove, I mean, people doing dynamical systems can prove, I think, that hardly, I mean, the measure of initial data that gives you that is 0, probably, in general. But we want more than that. We want quantitative estimates with respect to epsilon, with respect to the number of particles. So the exterior of a convex domain, it looks pretty reasonable that once two particles meet, then they meet the boundary, then they leave forever. You never see the boundary again, so it should be okay. Of course, okay, it's not so easy, but you expect maybe it's less hard. But if you look at anything else, then you might have trapped trajectories, all kinds of horrible things. So that's why people have never really tried that. Really, I have at least never proved anything about that.
The second question in the chat.
Yeah.
Chat.
So let's see. So the question is, do I understand correctly that a noise in the stochastic PDE limit is not space-time white noise, but the correlation is given by some function of a deterministic solution? So, so the noise in the stochastic limit is space-time white noise. It's not white in velocities. So let me maybe show it again if I can, if I see it works. Here it is, right? So the noise that appears here is white in space and time, right? You see in X and T, it's just direct mass, well, just Lebesgue, right? X1 is equal to X2. So it's white in space time, but in velocities, you have this correlation due to collisions, due to recollisions. Okay, actually, so I said you're supposed to be surprised by that. Actually, you're not supposed to be surprised once you've understood the thing, because even if you're at equilibrium, you have this, maybe some of you know that, fluctuation dissipation result saying that you have to have a noise to compensate the fact that the linearized Boltzmann equation dissipates energy. Okay, and so this general principle that says that you have to put a noise to compensate that. So even at the level of the equilibrium, you'll have a noise, but it's much more involved in some sense at the level of non-equilibrium. It involves recollisions. It's more subtle, but still it exists all the time, actually, this noise. And it is space-time white noise, but correlated in velocities. Yeah. Hi, Alexis.
Yeah, please ask you, in your proof, in the case where alpha tends to 0, what is the convergence rate? How does it compare
please
to the
don't
graph?
ask. It's okay, it's ridiculous. So maybe I can show you what the thing I skipped before. So the results where you can do both alpha going to 0. Sorry about this. Okay. So the case where you can do alpha going to 0 is linear situations. So the first thing you can do is start with just everything at equilibrium except for one particle. You let epsilon and n going to 0 and infinity. You get the linear Boltzmann equation. And at the same time, you let alpha going to 0 at the rate. So in that case, I didn't check, I forgot, but I think it is something like log n to the -1/4. I'm not sure about the quarter. Okay, so you're doing everything at the same time, n going to infinity, epsilon to 0, and alpha going to 0 at this rate. Okay, so this is hopeless, but that's what we get. And if you don't like that, you'll love the other theorem. So the linearized case, meaning all the particles are close to equilibrium, you get something like that. Okay, so if you can do the exercise of taking the Avogadro number and computing 3 logs, this is not going to infinity very fast. So this is very bad from a physical point of view. But okay, still, we're still happy because it's still a result. So you're still getting something. But our hope, I mean, right now we're trying to get rid of 1 log, to be honest. We're trying. I mean, we're far from getting rid of 1 log. We're pretty sure that getting rid of 2 logs will be very, very difficult. 1 is probably technical. The same way here, getting rid of 1 might be possible, but 2 might be very, very hard. But yeah, so that's a rate of convergence.
Yeah, please ask just 2 slide follow-up questions. So firstly, this scaling, is it in order to allow you to control factorials from growth of graphs?
Yeah. What's happening, 2 logs is exactly that. Let me try to remember. What you're controlling is the size of the trees, which is like epsilon to the t, and that seems reasonable if you're not better than, if you don't look more at the physics, a tree will grow like an exponential. And then you're controlling all your collision terms, and they will like some not really a Gronwall, but more like a, well, you lose an exponential just by this control of the collision integrals. You get c to the number of particles. Okay, and since the number of particles is growing like e to the t, then you get a double exponential. Okay, so what we hope is to be able to kill 1 of those. But yeah, it's combinatorics that's out of control.
And perhaps from a more philosophical point of view, so in hopes of being able to control the derivation of Boltzmann equations for longer times, for ever longer times, would it be reasonable to assume that actually that will not be possible for the Boltzmann equation in its basic form? But in order to be able to control longer times, one actually has to modify the collision operator with more and more terms in order to actually capture the correct physics?
Yeah, okay, that's a very good question. I sort of have 2 answers to that. I think I agree with you that one way of doing that maybe would be even to put some noise in Boltzmann, right? Fluctuations are there now. We know they're there. Maybe we could add them to Boltzmann, write a correction to Boltzmann, which takes into account those recollisions which appear at the level of fluctuations. So maybe, yeah, so that's a good idea to say Q of FF is not enough. Let's make it more precise at some scaling. And that's a very good idea. So that would be a possibility. And another thing I think that should help would be for very long times. What I assume, and I think it's probably true, that if you wait for a very, very, very long time, whatever your initial data, you get Boltzmann. Even if your initial data at first was not chaotic, because you want to say that after a very long time, everything will become chaotic. Okay, some kind of ergodicity will pop up. I don't know why, I don't know how, but it has to happen, I guess, for a very long time. So what I understand from all this is probably for short times, if initially you're chaotic, then for short times, not ridiculous times. I mean, particles have met, right? But still for short times, you're still chaotic. Then probably what you're saying is true. Something happens, so you have to be more precise maybe in the physics to continue controlling the equation or controlling what's happening. And then for very long times, whatever you have to add probably disappears because something else has come in, which will give you again chaos. So maybe there are several scales, right? This is totally, I have no idea of anything I'm saying here, right? So yeah, I agree with you that probably at least for intermediate times, something probably has to be done on the right-hand side to fix Boltzmann, maybe.